Oh, what's up? What's up? Today we're working on my custom operating system, working on implementing interrupts in my custom Rust kernel. So this is a continuation of where we got to last stream. And last stream we were looking at uploading the GDT to the CPU. So what the hell is a GDT? Good question. So if I pop open this like Intel manual, boom, 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 here we go. There is this concept called the global descriptor table, and let's see. So on a CPU, all memory access goes through this global descriptor table, and this basically sets up like what we can do in terms of like memory access. So, you know, it'll say like, oh, you're in kernel mode, so you can access kernel memory. You're in user mode, so you can access user memory. Or this process has this memory range and this other process has this memory range, which lets us like handle permission switching well. And also, importantly for interrupt handling, allows us to switch contexts through the interrupt. So the interrupt will say like, hey, I point to this piece, this permission level, and this chunk of memory, and that's where the interrupt triggers. And the CPU does like automatic handling of permission switching, etc., and then also handles like switching back to the permissions levels. So that's what we want to do today. Let's just quickly show what where we are right now. So I forgot to pull. Hold on a second. I have to mount my Git repo. So let's just do that over here real quick. 1 second. Okay. Cool. So where we are and where we got to at the end of last stream is that we uploaded a GDT to the CPU, and we gave it like a couple segments here. We gave it like the null descriptor, which is required, as well as 2 chunks that basically these bit flags mean like you are allowed to use all memory, but in this mode you're only allowed to access executable code. You're only allowed to execute code, and in this segment you're only allowed to like read write data. So that's this like enforcement of this like W XOR X security thing. I don't really know why it needs to be this way, but it seems like the CPU has it built in, so it is what it is. And this has some like obvious benefits where you can like prevent a virus from updating what code's can be run without having to go through some like major hoops and stuff. So that's where we are right now. So we uploaded the GDT to the CPU. However, we have not yet reloaded it. So this is a prerequisite to getting interrupts working. Reset to interrupts. Because hold on. Because interrupts need to happen in a GDT context. So let's just quickly drop in here that what's the other part here? Yeah, okay, that's fine. So this is where we are, and what we want to do next is, so now we want to work on reloading the GDT so that we can use it in our interrupts. So let's pop open the osdev GDT tutorial, I think it's called. Right, and so what they tell us to do is disable interrupts, fill the table, tell the CPU where the table is, and then update. So we've only really done these 2, so I want to quickly bang through getting interrupts disabled and then reloading, which I think is pretty easy. So they say that on initialization, we should, hold on. Yeah, okay. I am just double checking that I'm up to date. Okay, so first of all, let's switch this back to the syntax I'm more familiar with. So option ATT syntax, which means we need to replace these square brackets with round brackets. This is like the ATT syntax way to dereference, or basically like get the memory address that's load from the address of memory that's stored in the register. Where like the square brackets were the Intel way. But I struggled with that last stream, so we just switched to Intel syntax. But I think, if I understand correctly, this should still work. So here we see that like we're not crashing. Things are being printed to the screen as we expect. So I think we're like in a pretty good spot there where this is working as intended. Okay, so they say we need to like clear interrupts, then re-enable them after updating, and then we also have to execute a jump. Here, let's see where it says. So this is disable interrupts. We can disable them with the CLI command. We can re-enable them with the STI command, which I think, or is it SLI? CLI STI, I think it's called. Yeah, STI are privileged instructions. So clear interrupt and set interrupt is my bet for what those stand for. Then here's the tricky part. So there are these registers that point to segments in the descriptor table. So in our descriptor, we have like a kernel mode code segment and a kernel mode data segment. And it's like, how does the CPU use these? Well, there are like special registers that point to these areas in the table. And the CPU checks the constraints on them. So, and it might even auto update them. So when I execute a jump, it will actually reload this code segment with the argument that I pushed in. So I think that gets put into the CS register. Where does it describe these guys? OSDev wiki CS DSES. Let's just see if that comes up somewhere. CPU registers, here we go. Okay, yeah, here. So these segment registers point to different areas of my table that we've set up, which are just these guys. Oops. I think that the clear and set interrupt stuff I just added to the assembly. Screw this up. Yep. Okay, so this is what we get from grub, and this is what we have right now. So basically we want to point to the code to segment 1 and everything else to segment 2. And I'm getting that info from just looking at the initial state that we're passed by multiboot /grub/qemu. So what they just say is that CS, the code 1, must be pointing to a read execute code segment of offset 0 and limit 0xFFFFFF, and all of these guys point to like the other data segment. So let's do that. So what we would have to do is to get the code 1 set, we actually need to execute a long jump because there's no way to set that register manually. So I think that the syntax was like jump to a specific address, which was like, okay, let's look at the jump, x86. Instruction. Segment and absolute address, offset. Maybe let's look at the example on here. Aha, yeah, so here they say jump to this label with this segment offset. So I know that my segment for code is at like 0x08, I think. And I just want to jump to like a label that's right after. So I'll just call this reload CS like they did. And here I can say reload CS. And then this is the same thing where I put a value into EAX. So let's give it a register that has nothing in it, but we know we basically need to like allocate a register for use in here. So let's call this GDT is this, and we'll call this segreg is this, or datareg, I guess. And this guy can say GDT. And in here, we can say move the value of 10, 2 segments in, hex 10, into data reg. And then we move data reg into DS. Here, we just put some percent signs here, E, F, and G and S. So theoretically, this should work, except that this doesn't like using named labels. It only wants to use labels of the form number. Oh, I also think that I had to prefix this with a $sign, if I remember correctly. Not sure there. So what are they saying? Form number, see this. Any reuse of a name label, local or otherwise, can result in assembler or linker error or may cause other strange behavior. Reuse of a name label can happen in a variety of ways, including explicitly, implicitly. Right, so if we use the same label in multiple ASM blocks, that's going to cause a problem. So they're claiming you should only use local labels in inline assembly code. Okay, so here's an example. Okay, so let's try that example first. So let's, how do I comment? Like this, I think. And let's just try their example first, where they call branch numbers with forward and backwards. So if I say like 1, I can do branch 1F here, and it should give me the right thing. Let's just full delete this for now, I guess. We can always get it back later. Cargo check. And it doesn't like this. Okay, so that compiles. Does jump compile like this? Cool. And does jump with a segment specified compile? Yes. Okay. So I think that's actually all we need to do. CLI, STI, and then we pull those moves back. So that was like this, where we had this now gets a label of 1. This jumps 1F. And this is all good. So can we run that? Didn't this just work a second ago? Am I crazy? Right? Like, this just worked, right? I did this? I did. Cargo run? Oh, cargo check doesn't compile it. Okay. So let's try again. So they had branch 1F. Cargo build. Invalid instruction mnemonic branch. Jump? Okay, so that works. But jump with a segment specified does not work? That's annoying. Unknown use of mnemonic without a size suffix. So jump local assembly, how do I call this? Jump instruction. We have that loaded here. So far jump is the one we're using, I think. So far jump local label. Oops. oops. Far jump, local label, and what's the error? Unknown use of instruction mnemonic without size suffix. Oh, so here. Oh, oops. This should be immediate. And I guess probably we can do like let's just use a global label for now. I think we can we'll call this reload segment regs, and we'll jump to that. So reload segment regs, and we'll make sure that this is working first, and then we'll get the rest going. So let's load these guys, which was bump. Where were we? GDT tutorial. Here we go. So we move 0x10 into this we called like reload reg, we'll call it, which is a output. We'll call it an output just to say that like you have to allocate one. And here we move reload reg into, what is it? DSES, ESFS, DEF, GS. Okay. So now it's getting mad, but we can just enable this feature in main for now. Say, you know what? We know what we want to do. And let's see if running this works. So we are just hot looping, which means that we've done something wrong here. So let's start by removing these interrupt flags to see if that's related. Okay, so it looks like it is, where clearing interrupts, we're crashing when we re-enable interrupts. Yeah. So why is that? STI, I think it's called a triple fault, when it just like fully reboots. Yeah. Basically, I was loading a GDT twice, once in the bootloader and once in the kernel. I don't know what I thought I needed to do, but it's okay. That's not helpful. So he probably just like fucked up his GDT. That's probably also what I'm doing. Triple fault when loading the GDT. Oh, this guy's doing something like very similar to what I'm doing. That's pretty funny. This is like very similar code. Okay, so I guess let's just double check. So our GDT is in fact being loaded correctly. Is it because my code segment is not readable? Well, okay, so let's see what happens. Do I crash if I just load the data segment into here? Yes. Okay, so the fact that like this jump is working and that the jump working is like a really good sign. Let's just try clearing and enabling interrupts. Does that crash it? It does. That's also a good sign. So that means that it's nothing wrong necessarily with our GDT. It's like something we're just not handling right. So I wonder if how do I say this? I wonder if interrupts are enabled at all. So let's just double check that commenting like this does in fact disable this, and I'm not sure it does actually. No, these don't work. So can I like comment in here? Can I do like this? Yep. Okay. So let's see if like just STI here fucks shit up. And it does. So I wonder if just interrupts just are never enabled. Can I check that? STI QEMU. Not QEMU, sorry. STI x86. So we want to know, do we have interrupts enabled? Can we check the interrupt flag? So check interrupt flag x86. Is a flag bit in the CPU flags register. So can I read the CPU flags register? Removes a word. Can I like push F? x86 read flags register. I don't. Here we go. Move EAX flags. Okay. So let's do that for now. So let's drop this, and here we'll just do a, we'll say, flags is here, and we'll say in an ASM block, we'll take the flags register and put it in the flags register that we're allocating from here, and then we'll say flags equals out reg and mute flags or something. Is that how this works, or do we just write flags? And it's probably like a U32 or something. Is assigned to but never read. Yeah. Okay, so this is working correctly. So now we can do print line. Like this flags. And maybe just for sanity, we'll set this to 0. And if we see 0, then we'll know it's broken. So let's say flags is this. It doesn't like that. Unknown token expression. Oh, because I forgot to enable ATT syntax. Unknown use of instruction mnemonic without a size suffix. So maybe it doesn't like this, like flags. Flags. Oh, this is a question. I'm an idiot. Some flags can be set or cleared. For reading or writing the sign, blah, 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 you have to load the lower 8 bits into the AH register. Haha. Load flags into AH register. Okay, so LHF. And this guy needs to be AH. And this guy should be an I8. U8. Explicit register arguments cannot have names, so this, oops, oh, here we go. This equals sign goes away. And, haha! So flags is 0x46. And which of these many flags is the interrupt bit? So CPU flags register. And I actually want to call this a U8 because that just works nicer for me. Nice. Oops. But that's okay. It's still printing what I want it to print. Why is it crashing when I do that? Interesting. Was this the same? That's very odd. I guess it only... Huh. That's weird. Okay, we'll assign it to an I8 for now. And then we'll cast it to a U8 for now and get bit. 9. What the hell is going on? Am I high? What's happening? So I load this into flags, into AH. How come this is only failing after I try to read it? Very odd. Flags. Can I like... Well, yeah, what isn't it like here? Oh, maybe I can't load. Maybe it's using the AH register here in a way it's not supposed to. AH register. Is the AH register special? The top half of AX. Huh. Bits 8 through 15. The top half of AX. So AX is composed of AH, AL halves, and is now the low half EAX. The upper half EAX isn't blah blah blah. Leaves other bytes unmodified for historical reasons if it has to merge. Oh, okay. So I wonder if, like, I don't know, does this do anything? Flags 2 as U8. Get bit 9. Yeah, I don't really understand why this is behaving this way. Something is not working the way I expect. So if I disable all this code... Oh, it is still just crashing. Let's disable some of this. Okay, so that's working. So maybe it's related to just like printing too much to the terminal or something. So let's try this again. Do we crash? Looks like yes. What if I don't do this? So that, yeah, that's very odd. Very odd. So something about using flags this way is causing problems. What if we do something like AX into EAX? Is that legal? I cannot be used. Oh, here. Oh, am I? Oh, yeah. So we move AH into EAX. And we make this a U32. And see if that works. So no, it doesn't like that. We can do this. No, we can't do that. I would like to know why this is crashing. I wish that there was some way to know. LAHF triple fault. Let's just... I don't know. So what's this instruction do again? Load status flags into AH register. And inline assembly in Rust, does it let me specify that? Maybe it doesn't like the AH register. Inline assembly Rust registers. Okay. Yeah, it does not claim that I can use that. Oh yeah, here, x8632, here, reg byte. Register class reg byte. And I can, in fact, pass that in. So what's the problem? What is the problem? Right? Like, hey, how's it going? Not bad. We're trying to understand why our current OS if I enable interrupts with this like STI command, my machine just like crashes. I'm trying to understand why. So here we're working on loading this like descriptor table into the CPU. Yo, what's up? And what they say to do is we're supposed to like clear interrupts, load the descriptors, set a bunch of registers, and then enable interrupts again. And what I'm finding is that like if I take this command out and run this, oh, oops, left in some shit here that I didn't want. Does this work? Yeah. So if oops, this is all commented out. Obviously, it'll run. Right. So if I do everything up until enabling interrupts, my kernel like runs and it prints stuff. Just doing some programming. Yeah, dude, that's right. Did I try building like a database or implementing a research paper? No. I am just writing an OS for fun. No databases or anything yet. My OS is like absolute trash at the moment. All it does is, oops, it crashes there. Where all it does is it prints, all it does is like allocate RAM, basically. We have like an allocator, stdio, to VGA and to console. And we have like memory allocation, so we can use like Rust like vector types and map types, and we can like load the time from the RTC. But above that, we don't do anything right now. So we're kind of building like the base of the OS at this point to try to like get into a state where we can start building something more complex. The end goal here is that we want to be able to run some form of like web server or something just to prove that we've got the concepts down. Yeah, so where we're at now is why doesn't this STI work? So in fact, we should probably write this down here. Why can't we enable interrupts? Okay, and so what I've read so far is that I want to know like what state my CPU flags are in right now, and so I'm trying to pull that info out. Oh, good catch, Jeff. The OS must good catch. The OS image must leave interrupts disabled until it sets it on IGT. Okay, yeah, that's sick. Good catch, good catch. Damn, you're reading. So the fact that this doesn't work is just expected at this point. I do still want to know why I can't read the CPU register flags. Like, I wanted to be able to like read this out and print out that interrupts were disabled before I did anything, and then that would give me like some form of like confidence that this is right. But then I started like faulting on some pretty straightforward code here, so I didn't really understand why that was. But I was printing this okay at some point, so maybe I can just check that manually. So this was take an i8 here, run code, and I get my flags as 0x46. So we can just open Python and do like 0x46, shift it left by 9 and 0x1, and this should tell us if interrupts are enabled, and they're not. Okay, so thanks, Jeffo. Good catch. So we know that interrupts aren't disabled before we start, and so we don't have to re-enable them at the end. It would be nice if we could like use that info in some way here, but for now we'll just assume that we can, whoever calls this init code, we'll say is responsible for enabling and disabling interrupts beforehand. So we'll mark this unsafe and just right above it, caller responsible for setting interrupt flags. And maybe what we can even do here is we could probably go back to reading that for flags. ASM. We could do this. We could say load the CPU flags into the AH register, and we'll say CPU flags in I8, and we'll say that AH goes into CPU flags. And then we'll say if CPU, or we'll just assert that CPU flags are off. So or that the interrupt bit is disabled. So CPU flag shift left by 9 and 1 is false or 0. Oops. Oh god, what did I do? Oh god. CPU shifted left by 9 and 0x1 is 0, and we just have to assert EQ. Okay. I forgot a semicolon here. And oh, set bit 9 is not valid. That explains why I was so confused. So the flags register bit 9. So why? I guess this has to be an I16. But we cannot use the AH register. So we actually want the upper half. So where's the LAHF? Load status flags into AH register. Oh, aha. Okay, so I want to load CPU flags register. How do I get it? Example, pop flag, push and pop flags register lets a program manipulate the blah, blah, blah. So pop F into the flags register, push F. Use a stack to transfer the flags. Aha! Aha, okay. So push F and pop into CPU flags. Haha! That's what I wanted. And then here I can just say this is a register, and this can be an I32. And we do like this. Okay, that's not working. So let's disable this stuff. Assertion failed is writing borrow. Interesting. So something, maybe we're just like corrupting something somewhere. This does seem kind of fucked. Push F, use the stack to transfer flags. Pop AX. Oh, okay. Maybe I need to restore it. Yeah, there we go. So now we can check that this is valid. Nice. Okay. So now we have sanity checks that the caller of this is setting interrupts. And so I wonder if I can like put a label here like caller is responsible for disabling, enabling interrupts. Does that... Oh, I need to make this assertion fail temporarily. Okay, yeah, okay, I'm happy with that. So now we have a function that initializes the GDT. We double check that interrupts are disabled, and now we're in a spot where we can all of this is loaded. Yeah, we're in a spot where we can just keep going now. Cargo run. Yeah, it's looking pretty good. Okay, so let's commit that. And we'll just call this checkpoint GDT fully initialized, as far as we can tell. And actually, we can actually double check that this is working correctly by intentionally breaking our descriptor table. So some of what it's doing is it's trying to check permissions, and we're setting specific permissions on it. So if we just say that like our code segment is not executable, like this, we should just get crashes now. Cargo run, which we do, which is sick. And maybe we can do something to like go back to main and print the GDT before and after. So here we see before we had 5 segments and now we have 3, and we know that when we change the access bytes, they're wrong. So I'm like pretty confident the GDT is working. So we'll say here that the GDT is fully uploaded. And now what's next? Trying to enable interrupts. So the first thing we need to do is figure out how to load the interrupt descriptor table. And what is that guy? This is very similar to the global descriptor table, they called it. And all it is we set up this table that we put on the CPU that basically tells us when a specific interrupt happens, i.e. like some hardware asked for us to service it in some way. It will load from our interrupt descriptor table what address to run, like to jump to. So it'll go like my CPU, we were like executing instructions, blah, 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 blah. And we're like, uh-oh, something happened outside. We like look in our IDT, I think. We like jump over here, check what address is in here. And then we like jump to that in code over here. And then when we're done, we jump back to here. So that's what we were going to set up next. Let's take a quick peek at the OS Dev Wiki, what it says about this. So let's... Oops, too many windows. Okay. So here we'll look up interrupt descriptor table. Descriptor table. And I think this is very similar to the global descriptor table. Yeah, this is similar, except that the first entry is used. There are 256 in the table. Even though it can contain more than 256 entries, they are ignored. And although the IDT can contain less than 256 entries, any entries not present will generate a general protection fault when an attempt to access them is made. And so at minimum, a general protection fault should be handled. Okay. So I guess we can probably just start there. So probably, I guess we can maybe guess what was happening before when we were crashing. Maybe when you enable interrupts, I wonder if that propagates interrupts that happened while we had them cleared. And if that's true, then we would just be hitting that unimplemented interrupt, and that would cause the reboot. Maybe. In some implementations, when interrupts are not enabled until after an extraction, in this case, sequence of blah, blah, blah. Yeah, okay. Well, we'll just guess that for now and kind of move forward and see what happens. So, what's next? Let's try to implement this IDT. So, the location of IDT is kept to the IDTR register, which is very similar to the GDT register that we just loaded. Loaded using the LIDT assembly instruction, whose argument is a pointer to an ID descriptor structure, which has a size is 1 less than the size of the IDT in bytes, and offset is the linear offset of the table. Okay, cool. So I guess the first thing that we want to do is set up the table, then we can set up our pointers to work with the table. This is similar to GDT, we already did this. On 32-bit processors, the entries in IDT are 8 bytes long in a form of a table like this. Okay, and each entry is a gate descriptor, which has an offset, a segment selector, some shit that we won't use, or that's reserved, unpopulated, etc. Gate type, which is one of these. So here, okay, so we can just start working with this. So let's just get right into it. So if I make a new file, source IDT or interrupt maybe. Here we're going to have a structure that's very similar to the GDT. Oops. I have this open twice, so I go back. So in our GDT table is modeled as something in static memory that we can upload to the CPU. I said upload to the CPU is wrong. We can upload a pointer to the CPU. So in this case, source interrupt. In this case, we don't need like dynamic memory. Here, our GDT table was using like a vector because we didn't know how many segments we're going to use. But here we know exactly what it is. So we can just say static. But we still do need this like mutability for when we register and interrupt handlers. So let's say that we have a struct that's a interrupt descriptor table. And this is going to have something that's going to be mutable in the static context, and each element is going to be like an IDT segment. What are they called? Gate descriptor? Yeah, we'll call that gate descriptor. Gate descriptor. Descriptor. And in main, we need to import this so that my indexer will tell me what I'm doing wrong. Mod interrupts, like this. And now we have to define the gate descriptor, which is just a wrapper around a U64, because this is 64 bits long. Consider importing this struct. We need core cell ref cell for interior mutability. And now we say static interrupt table is an interrupt table equals interrupt table new. We construct a new one, which means that we need to implement new. So we do that really quick. Say function new returns a self. And here we return self with an inner value of ref cell new gate descriptor 0. And this is wrong. This actually needs to be an array of gate descriptors that's 255 entries long. Gate descriptor we need to make sure is like packed. I think that maybe I don't need to type this, but just for how do I say this? Just for my own comfort, I'm gonna say, please, like, don't fucking touch my bytes. This is spelt wrong. This needs a. We need what? We need to put this in an array that's 255 inches long, like this. And this is saying that it doesn't like that it can be shared between threads. And it's true, this can't be shared between threads, except I know that my OS only has one thread right now. And so I can just say, hey, Rust, please just like ignore the fact that this is non-shareable and do it anyways. There we go. And now we need to derive some things on this gate descriptor. So we'll derive copy, we'll derive clone. And we can't call some statics, but I can if I just write the word const here. Okay, cool. So we're chilling there. We've got our static interrupt table set up. And now all we have to do is like figure out how to populate it. And so we can construct a function that takes in the like things we care about and generates a gate descriptor. And let's just kind of see what those are. So we care about the offset, which is 32 bits. We have a segment selector, which is 16 bits. U16. We have a gate type, which is 4 bits. DPL, which is 2 bits. 2-bit value which defines privilege levels. Yep. So DPL. And we have the P bit. And what's kind of nicer here is if we, instead of having these as parameters here, we can create a struct gate descriptor new args and put these in here. And the reason to do that is when we call it, we now get to like call with each of these named instead of just like passing them in as arguments. And that makes it like a little clearer at the call site what the hell is going on. So we'll bring the spool. And in here, we'll take in descriptor new args. Okay. So now our gate descriptor is a U64. So we'll say, we'll create a new U64 that's just nulled out for now. And we'll just set all of these bits based off of what we have here. So the first 16 bits are the first 16 bits of offset. So descriptor set bits, which we need to import from our traits here. So we have like this like utility struct or utility trait that automatically sets like chunks of bits, I guess we should say. We can set like chunks of an integer. So let's go take a look at that. So let's create util bit manipulation get or set bits, I guess it's called. And all this guy does is he takes in like how many bits we want to set at what position and what their value will be, and he'll just like construct a mask that and assign the value to those bits. So for example, we can call this with the offset. The shift is 0, the length is 16 bits, and the value is args offset truncated like this. I guess I don't really like it. And we need to make this mutable. And why doesn't it like this? Into a U64. Oh, oops. It actually has to be upcast. That's fine. And the upper bits are set at bits 48 to 63. So do the same thing, except we shift it by 48. And we take the lower 16 bits. So we say lower args offset shifted by 16 as U64. Now we can set the segment selector. So that's segment selector is at shift 16 with 16 bits, and the value is just arg segment selector as U64. 32 to 39 are reserved, 40 to 43 are the gate type. And if I remember correctly, what I was reading is that trap gates and interrupt gates are similar, except for trap gates can be run in user space and are like software triggered, and interrupt gates are like the kernel space one. So let's just assume for now that I want to do a 32-bit interrupt gate, which means 0B1110. And this gate type goes to shift 40, length 4, and we take in args dot gate type. As U64. And now we need the DPL, which is 2 bits at offset 45. So we do this and DPL. We have the present bit, which is at 47. It's 1 bit, and it's P. And then we're done. We've set them all. Offset, segment, gate, DPLP. Yep. Okay. Now, what's next? I guess that's it. We just need to now add a an interrupt handler to the table, and then load the IDTR. So loading the IDTR is by using this structure here. So we'll say struct IDT has a size at the bottom 16 bits. So that's a U16, and a offset, which is 48 minus 16 is 32 bits, which makes sense because it's a 32-bit operating system. We'll say, please make this packed. And then we can make an initialization function here. So pub function init, this will be called my main, and this is going to initialize the interrupt table to put in some descriptors somehow. So let's do that. So let's do what they said that we should. Somewhere they said something about like the general interrupt handler. Where did I see that? Where did I see that? General protection fault. So let's start with this. So what is the general protection fault here? Aha. This is vector number 13, and this is a type fault, not interrupt. Okay. So I guess let's just try to handle this and see what happens. I think I saw somewhere as well that I can't just use like a raw function to, like, I can't like write the function in Rust and pass the address to that directory specifically because of this like iReg shit. And I think they said somewhere that in this page they're like, you might be tempted to do it in your OS language, but really you should fucking do it in raw assembly. I think I saw somewhere about like there are maybe attributes for defining a function that will use iret instead. So I think there's like GCC attribute interrupt. Just give the Google a little second to load. Yeah. Just attribute IRQ. Use this harm AVR. None of this says x86. To indicate the specified function is an interrupt handler, the compiler will generate a function entry and exit sequence suitable for use in an interrupt handler when this attribute is present. Yeah, this is what I was looking for, but this does look not x86, but it's similar. So I wonder if Rust has something similar. Rust interrupt handler function attribute. Ooh, yeah, nice. They do have, I can just write interrupt. All right. So let's try that. If I go here, let's write a like general fault interrupt handler and just write interrupt like this. Cannot find attribute interrupt. That, honestly, I don't know why I was expecting anything different. Right, because this interrupt comes from a crate here to generate interrupt handlers automatically. What does this do? So, yeah, that's not what I'm looking for. Use a crate. Good catch. I'm looking for this. Oh, just put a quote on it. Thanks, Switch. This is exactly what I'm looking for, and it looks like not implemented. Considering this is open. Okay. Good catch. Japfo, have you done this before, or are you just like rapidly Googling in the background while I'm talking? Okay. So I guess we'll Ooh, it's in nightly bound of feature flag. I do like that. Oh, you've done it before. That's fun. What for? What were you doing? Okay, yeah. So feature gate name is ABI. Aha, nice. So here I can just enable this feature. Cargo check. Okay. And then I can go to the IDT section or interrupts, and I can specify this as extern x86 interrupt function. Nice. Whew, thanks, man. I think I probably wouldn't have found that. I would have done something different. That's pretty sick. And this takes in a stack frame. And probably exception stack frame comes from some core library, and for interrupts and exceptions without an error code. So probably if I look up exception stack frame in the Rust docs, nothing. Nothing at all. So where does this guy come from? See the proposal. That's not really what I want. I just want someone to tell me where the types are. Okay. Oh, what is this not done? 32-bit mode, the CPU applies no alignment on interrupts, thus the interrupt handler should perform a dynamic stack alignment, i.e. and ESP16. However, LLVM doesn't do that, which might lead to alignment errors, specifically for targets with SSC support. Okay. It's worth keeping in mind. Known issues. Say that is passed by reference to value. I wonder where that comes from. Like, use core arch x86 exception stack frame core arch. Well, I guess we can just not use this for now and see what happens. So let's just print hello in here for now. I don't know if printing from an interrupt is valid, but I guess we'll see. What we could do instead is we could try like incrementing an atomic and printing that and seeing if we see something there. Okay, so on init, we probably want to set the general fault handler to this gate descriptor. So we need a new descriptor. We'll call this let general fault descriptor equal gate descriptor new with the gate descriptor new args. And now we just set all of these fields for what makes sense here. So this is a fault. And okay, let's see here. The offset is a 60. Oh, oops, wrong section. Offset is a 32-bit value split into two parts that represents the address of the entry point of the interrupt service routine. Let's look up this interrupt service routine. What the hell is this? Interrupt-driven system, blah, blah, blah. Such events may be triggered by hardware or software. Yep. The problem. Many people should away from assembly. Right. This cannot work. The compiler doesn't understand what's going on. So I guess theoretically, this x86, this attribute for interrupts, theoretically fixes all this. Because it's the same thing as using this. Oh, okay. And here, this is the frame that they were talking about. Does that mean that I haven't... I wonder if that means that I have to, like, handle these correctly. Blah, blah, blah. Where does it say... what to do with this frame. Let's try just ignoring it and see if that crashes or something. And if it does, then we'll loop back. So, okay, I think theoretically I can just use the address of the general fault handler here. Can I do this as like, oopsies, as U32? Wow, that actually does work. I was kind of not expecting that. My selector is a segment selector, which is this. So the index is the upper values of the index. Right, because they're always a bit aligned. So well, let's set this guy up. We'll start him as a U16, I think it is, with a value of 0. We'll set the top 16 minus 3 is 13 bits. That took me a second. To this shifted left by 3. Is that correct? I think so. We'll see. TI is, we want it to be 0 to use the GDT, so we don't have to set this. And RPL is the privilege level. And I assume that we can just write 0 for ring 0. So I assume that this is actually fine. So I can actually just write 0x10 in here. Because we are fully in kernel mode. Gate type, this is a 32-bit trap, so 0B1111. Oops, this is not DPL, this is gate type. P has to be true. And DPL is a CPU privilege level, so probably just write 0 again. Okay, so now we have a fault descriptor, and we just need to slot this in at the right spot. So that's 13, 0 indexed. So we can say interrupt table dot inner borrow mute. We want to set table 13 is equal to general fault descriptor. And then what's next here? Now that this is in there, I guess we can just load it and enable interrupts and see what happens. How to program this stuff? Make stuff for the interrupt table. Tell the CPU where that space is. So LIDT. Tell the PIC that you no longer use the BIOS defaults. Write a couple of ISR handlers. Put the addresses in the appropriate descriptors and the interrupts. Enable all supported interrupts in the IRQ mask of the PIC. Okay. So I guess that means that we need to program PICs first, actually. Let's look at this. Programmable interrupt controller is the one most important chips making up the x86 architecture. How do I program it? So there's I/O ports for the interrupt controller. And there, so it looks like I talk to it and I tell it what maybe I want to clear interrupts on it as well. What does it do? Controls the CPU's interrupt mechanism by accepting several interrupt requests and feeding them to processor in order. Right. For instance, when a keyboard registers key hit, it sends a pulse along the interrupt line to the PIC chip, which translates the IRQ into a system interrupt and sends a message to interrupt the CPU from whatever it's doing. Part of the kernel's job is to handle these IRQs and perform necessary procedures. Pull the keyboard for a scan code, or a user space program to the interrupt. Sure. Without a PIC, you would have to pull all devices. Okay. So, do traps go through here as well? Maybe I can get this running initially with just a trap handler without programming this. And I do need to tell it I no longer want to use BIOS defaults. That's actually big. So I do, in fact, need to program this. So how do I do that? So this is claiming that I have 2 PICs. So in the beginning, there was only one, which provided 8 IRQs. But we will not encounter those. Instead, we're going to hit the extended architecture by adding a second PIC chip. This is also possible due to the ability to cascade interrupts, flow through one chip into another, gives a total of 15 interrupts. Why 15, not 16? Well, when you cascade, you lose one of the interrupt lines. Sure. Thus, in an AT, IRQ2 is used. IRQ line 2 is used to signal the second chip. Because this IRQ2 is not available by hardware devices, which got wired to IRQ9 on the slave PIC instead. The real mode BIOS used to set up an interrupt handler for IRQ9 that redirects the IRQ2 handler. This way, DOS drivers. Yeah, okay, sure. So, is that still only 15 interrupts? Yeah. Okay. So, I have these 2 PICs in series. And I can talk to them individually. But I guess I still only have like the 15 IRQ. Oh yeah, here we go. Okay, in protected mode, IRQs 0 to 7 conflict with CPU exception, which are reserved by Intel up until. Consequently, it is difficult to tell the difference between an IRQ or a software error. It is thus recommended to change the PIC's offsets, known as remapping the PIC so that the IRQs use non-reserved vectors. A common choice is to move them to the beginning of the available range. So I guess probably here, when they're saying that I no longer want to use the BIOS defaults, what this actually means is just like tell it what you fucking want. I'm assuming that's what it means. So here are some claimed reasonable defaults maybe. So when you enter protected mode, the first command you'll need to do is the first command you will need to give the 2 PICs is the initialize command. Sure. So we initialize them both with 0 and 1. This command makes the PIC wait for 3 extra initialization words on the data port. These bytes that give a PIC its vector offset, tell it how it's wired to master slaves, gives additional information about the environment. For example, buffered mode, I guess. So here they initialize. What's ICW4? Indicates that ICW4 will be present. I see. So here they're saying, here we're going to initialize you, and you're going to get the extra info. Then they do the same thing on PIC 2. We tell PIC 1 that it's going to be offset by some number, and we tell PIC 2 it's also going to be offset by a different number. Offset to ... offset to. Okay, sure. I guess you might want those in different ranges for some reason. Okay, sure. Then you say, tell the master PIC that there's a slave PIC at IRQ2. So this is just a hard-coded number. I would be nice. Maybe I should like pop open the docs for this at some point, but sure. Then they tell the slave its cascade identity. And here, the extra info is that we want to use 8086 mode, not 8080 mode. So I wonder if there's like a spec sheet for this thing I can look at. Like data sheet for this thing. Programmable interrupt control. So this does look like what I want. And somewhere it will tell me what these data lines that I can write are. Where does it tell? So none of these tell me about the initialization, or I just missed it while I was skimming. Oh, here we go. Initialization. Yeah, this is what I was looking for. Initialization command words 1 and 2. So what was the thing that I was not sure about? I wanted to understand what this 4 is. So this is pick data 1. So this is initialization word 1, 2, 3, 4, or maybe 1, 2, 3, 4. Let's check. Okay, so initialization commands word 1 and 2 is page starting address of service routines. Address form is 2 bytes long. 8-byte interval, maintain compatibility. Okay. Right. So 1 must be the initialization. This must be 2. Then we can look at byte 3 is when there is more than 1 in the system. In which case single equals 0. It will load the 8-bit slave register. The functions of the register are in master mode, either SP equals 1, or in buffered mode, when MS equals 1 in ICW4, a 1 is set for each slave in the system. The master then will release byte 1 on the call sequence. In the slave mode, if buff blah blah blah, identify the slave. So where do I see these definitions for like what the hell SP is? Because that's probably where these numbers come from. Slave program enable buffer. Oh, these are pins. I want to see like the... How do they know to write a 4? How do they know? The word is read only when there's more than one. And in the system cascade. Oh. Read only. Oh, maybe it's this one. Level interrupt mode, call address interval. Single means that there's only one in the system. If single, aha. So A15 to 11 are inserted in the 5 most significant bits of the vectoring byte, and the 8 sets up the 3 least significant according to the interrupt level. I see. So this is ICW2. And how do I know what bits these are? This is... Ah, here. Okay. So this is 1, 2, 4, 8. So let's go back to this guy. And tell Mac that there's a slave at IRQ2. So this is the 3rd bit, which is ADI, call address interval. So that's not what I expected. Not what I expected. Because I would... 0 is cascade mode. Aha! So they're saying that there's a call address interval of 4, single mode, no ICW4 needed. No, this is the initialization byte. ICW1, ICW2. Haha! ICW3. IR input has a slave. IR input does not have a slave. And ICW4 has 8086. Yeah, so I guess... so that 4 is saying that one of these... the interrupt lines coming in are which ones of these have slaves. And since it's in cascade mode with a single one at IRQ2, we set the ICW3 to 4 because that will set only this bit. Got it. And so now what are they saying about the slave device? Oh boy. Tell the slave it's cascade identity. What the hell does this mean? Oh my lord. So this is the interrupts probably. And depending on which of these are set, it will behave differently, I guess. Not really sure. Not really sure. Where do they talk about cascading? Is this searchable? Cascade. God, this is complicated, and I think I'm not going to understand this very effectively skimming on stream. So I think probably what I'll do is I'll just assume that those values are right, and I'll come back to it offline and try to understand. For now, we can assume that we need to talk to these. So we'll say, we'll take in the port manager here. Right, and we'll use IO port manager, like this. And we will use this to initialize the pick. So here we say, where are our ports here? So pick 1 is 0x21, and that's command. So this is port manager request port 0x20, and pick 1 data is 0x21, and pick 2 data and command are A0 and A1. Like this. And then we'll set our offsets. So this is saying that we want, I saw somewhere, I can't remember where, that we want offsets that are reasonable. Let's just do like enough to get out of here. So we'll just offset like 0x20 or something. Sure. So let's say pick 1 command write B. Are these writing bytes or words or what? Looks like bytes. Yeah, because this offset is 16-bit, and we have to write it in 2 chunks. Okay. So we write the init, which is like this. Let's copy paste these in, I guess. Like this. We convert these into constants. So like this. Convert to constant, convert to constants. Okay. And we write here ICW init or ICW1, ICW4, like they said here. These have to expect that they worked. Failed to get pick 1 command. And this is pick 1 data, pick 2 command, pick 2 data. Now these write functions are available. And now we write the data line. So we say pick 1 data. We write to it a offset. So let's just make it like this or something. then we write a 4, and then we write a 2. Oh, sorry. Offset for ICW 8086. Like this. Is that correct? So we wrote initialize, offset, then we wrote the 4, then we write this. Okay. And then what is A1? Aha. So A1 was pick 1 data. Like this. And now we do the same thing for pick 2. Right, except the offset is going to be 30. And we're going to write it into slave mode. But other than that, it's the same. Okay. Whew. That was a lot of work. Oh, if you're gonna... I guess we could just disable this for now, actually. Maybe that's an easier starting point. Because then we just won't get external interrupts. So this is just the data ports. We just write AL. Is that because the masking is done by writing to the data ports? Maybe it is. Port equals pick 1 data, RQ, value equals NP, and yeah. So this just, if we just write to data without initializing, it should just be we can mask, we set up the masks, so we can just mask everything like this. So let's just do that. Disable external interrupts. Okay. Okay. So we tell the CPU where that space is. We haven't done that yet. But we have talked to the pick. Say, don't fucking touch us. Wrote an ISR handler. And we need to put the ISR handler in the descriptor. So we've done that. And enable all supported in the interrupts in the RQ mask of the pick, which we disabled completely. So now we just have to execute the LIDT ASM. Okay, and here we're just gonna say LIDT, similar to the way we did LGDT over here. We're just gonna load the IDT like this. And this is options HT syntax. And we need to import this. So use core, I think it was Arch ASM. Yeah, nice. Use core Arch ASM. Now we just need to construct the IDT. So do we already have the IDT type? We do. And so IDT is this. So what I don't understand is, why does the IDT need a size in it? Because isn't my IDT fixed at 255? Isn't that what they said? There are 256 interrupts, so the IDT should have 256 entries. So it's kind of odd that we have to specify this at all, but I guess it is what it is, and we'll just move with it. Oops, I just clicked something that I didn't mean to. How do I unpin this? Here we go. Oops. Okay, so we'll just set that size as full, which is 255. And like this, size 255, and offset is the address of table. So let's say table pointer equals table.as pointer, and this is a this should be a gate descriptor. And here we can say table pointer as U32. And there's no argument made up named IDT, so we can say in is an what was the syntax here? IDT equals in reg ID table and IDT. And maybe now we can enable interrupts. I guess let's start by not enabling interrupts and seeing what happens. So let's go to main, and we'll call interrupts init with port manager as an argument. And we'll just see if this crashes. Okay, so we are already missing some stuff. So this, we need to return gate descriptor. Okay, we can't borrow table as mutable. Makes sense. So, oh geez, everyone's mad at me. Okay, I forgot that this happens where you have to get stage 1 compiling before stage 2 compiling works. Cargo check. Okay, cargo build, cargo run. Okay, so loading this LIDT didn't crash anything, which is good. So let's do the same thing as we did for the GDT and try to read the register here. So this comes back with an IDT, and it's like this. And here we go. Let's print line the IDT before and after. So this is read IDTR, this. And I guess this needs to implement debug, like this. And we'll print it before. Okay, so that's good. We do have something. It seems likely that my size and offset are wrong, considering that previously I had size 1023, but that's okay. Let's see what happens if we set the interrupt flag. Oh, that's a really good sign. That's a really good sign. Setting the interrupt flag doesn't crash. And so now I wonder if there's a way to like int what is this handler? This is 13. Invalid operand for instruction. Right, because I need to put a little percent or a $sign here. Okay. So that's clearly crashing. So we're not there yet. But theoretically interrupts are enabled. So now it's time to debug what the fuck is broken. Oh, it's in bytes. This is the size in bytes times 8 minus 1. Okay. And let's try this now. And let's try int 13 again. I assume this will crash. It would be crazy if that worked. Okay. So now my size is 1023. Oh, sorry, that's wrong. So now my size is 2047 instead of 1023. My offset is here. Oh, this looks wrong. Offset. Oh no, offset is U32. General fault handler is a U32. It doesn't like that, but that's okay. I guess now we need to find some way to confirm if this is working at all. So when I run int 13, it would be nice to know if it is happening. Let's try, I wonder if we can like set like this at like 80 as well. Let's take this print line out for now, and let's try executing int 80. Okay. What if this is because I set this as a trap and not an interrupt? So let's only set it at 80. Or let's not set anything at all and see if we can at least enable interrupts. That's a good clue. Okay. So we can run STI, nothing crashes. So now, let's set this at 80 as an interrupt gate instead of a trap gate. That might be causing the problem. Which means that this needs to be 1110. And my segment selector actually should be maybe the code segment. And now let's try executing int 80. Oh! That's huge. We didn't crash. Okay, so let's try printing something in here. Oh, baby. Look at that. Look at that right there. That's sick. Okay. So that's really good confirmation that our interrupt handler is set up. We're like executing an interrupt. So there is a problem still where it looks like we like crash. I think that there's a invalid memory access in the VGA section. But that's really sick. So here, if we get too much output so we overflow and have to wrap back around, there's like some bug where it crashes. But this is sick. Okay. So we disabled masking, disabled all interrupts from hardware with pick mask. Oopsies. From hardware with pick mask. Enabling interrupts. So we disabled all interrupts from hardware with the pick mask. We set up the interrupt descriptor table. We loaded interrupt descriptor table into IDTR, and then we executed an interrupt and saw the results. Okay, that's absolutely sick. So let's checkpoint that, just so we don't lose it. We'll call this interrupts now runnable. And we'll go back and look at this interrupt stuff. Okay, so first, let's see if this crashes if we use this. So if we say it's a trap or an interrupt, it doesn't seem to behave any differently, which is interesting. In reality, this general fault descriptor should be at 0x13. So before, if I assign nothing, if I understand this correctly, and I try to int 80, this should crash because there's, yeah, that crashes because there's no fault handler. But if I say, hey, if you don't find anything in there, that did something absolutely fucked. Oh no. Okay, so I was gonna say that the fault handler should correctly handle the fact that this isn't implemented, that interrupt isn't handled. It should say interrupt 80. It goes like, oh no, we don't have 80, but we do have 13. But maybe I have to like return something. Like, do I have to issue an IRET here? Let's see. What do these guys do? Let us see. Exception, stack frame, interrupts, cause gibber. That's not what I want to see. Okay. Somewhere. Perhaps the interrupt calling conventions. This is unsound on 32-bit. When processors in legacy mode are pushed by the interrupt and pop by IRET, only if the interrupt crosses privilege levels. So I guess what we can do is we can just look at what is in this function and see what the fuck this is doing. So let's look at this, and it's called general fault handler. And let's see if this guy at least ends with an IRET. So he does end with an IRET. That's good. And probably these, like, I wonder if these, like, print lines are causing problems. Okay, so let's start by just doing nothing, right? So here, this clearly is not working as I thought. So what does the general fault handler supposed to do? Bump, bump, bump. Oh, maybe it's because I said this is a... Maybe I just said this is a trap. No, doesn't like that either. Where here, general protection fault may occur for the saved instruction pointer points to the instruction which caused the exception. Writing a 1. So these are all things that can happen, but like how do I handle it? Contain less than 256 entries. Any entries that are not present due to this or other reasons will generate a general protection fault. So how do I flag not present? Oh, I wonder if it's like trying to execute something stupid. So let's start by, let's see what happens if I reduce this length from 255 to 1. And here, this should be now table.len times 8 minus 1. As U16, right? And they do need to be handled in incrementing order. Do they all have to have valid? Oh, the fact that P is not set should mean that it knows. So I was going to say, like, how does it know not to execute just the code there? But the fact that P is null is, like, a good indicator. Okay, so then we're back to why the general fault handler isn't working. I guess it should be 256, not 255. Yeah, I'm not sure why. So this fault can be handled. Maybe when it says enough, here it says it should contain enough entries. So maybe it does think that 80 is valid. So let's say, what happens if we call, we take this 255 or 256 and we reduce this to, like 20, right? Just for sake of argument. And we call int 13. It needs this to be an immediate value. So that works. But int 22, this is not working correctly. And I wonder if, like, if I print something in here, it is in fact printing something there and then just fucking slamming through the binary, which is crazy. I wonder if I need to, like, move into a new scope because something isn't being handled correctly. No, that's not it. How do I get out of this? Oh no. Here we go. There's something that I don't understand here. But it is cool. So if I execute, so shit, let's move all these 20s back to 256. I'm not understanding something because, like, if I execute 13, oh fuck, cargo run, it works as expected. So I'm not understanding something about, like, the missing interrupt case. But we're definitely running an interrupt, and I can if I assign this to, like, 14, 15, 16, I can run interrupts at, like, any of these. So it's definitely working. And that means that, like, our GDT is also set up well enough so that the interrupt can load for it correctly. So I'm pretty happy with that for now. I'll probably do some, like, off-screen reading to try to understand this a little better. Clearly, there's something wrong. But we did manage to set up the GDT, get it uploaded to the CPU. We've confirmed that it was writing correctly. If we see this section here, we can definitely see, like, the segments are loaded, and we've also confirmed by writing invalid things to it. We confirmed that we were, like, causing faults and that it's being used correctly. So that's pretty sick. And then we set up some, like, interrupt handlers. We got the interrupt vector loaded. We have a function in Rust that is correctly running and returning back to the context that it was interrupted from. And the only thing that we don't have right now is what happens if we call an invalid interrupt. All of a sudden, that's like, oh, that's causing some major problems. So other than that, though, we made some, like, pretty good progress today, and I'm really happy with where we ended up. Thanks for watching. If you want to catch another episode, I'll be live most days at around 2 Pacific time, and you can always catch up on YouTube. Thanks for watching. Catch you in the next one. Bye.